Hey there. Today we'll be going over modular arithmetic, which is a topic that's shown up a couple of times in the AOC by now. There are some problems that you cannot solve without using it, and it's a useful thing to understand in general. It's used in all sorts of contest problems outside of the AOC as well. You'll also need to use it a lot in real-life applications. In fact, you've probably already used it. You just don't fully understand the extent of it. So in most languages, the mod operator is represented by the percent sign. So you might already be familiar with how this works. 7 mod 3 is equal to 1. And what exactly does that mean? Well, it means that when you take 7 and divide it by 3, you get a remainder of 1. So in other words, 7 is 1 greater than a multiple of 3. Now that's what the operator does in most languages. But before we start actually discussing the details, we have to go back to what modular arithmetic itself is, because this operator isn't really a thing in modular arithmetic even. So what is modular arithmetic? Fundamentally, it's arithmetic that operates on a different set of values than conventional arithmetic. So these values are still labeled by integers, but they're actually what are known as equivalence classes. So here's a question. Thinking in 24-hour time, what comes 4 hours after 23 o'clock? So that's 11 p.m. It's 3 a.m. the next day, right? So it would be 3 o'clock. But is that the same time as 3 a.m. today? It isn't, right? Because one of them is today, one of them is tomorrow. They're 24 hours apart. But they're both labeled 3 a.m. So they're part of what we would call the same equivalence class. And so that's fundamentally what modular arithmetic is all about. Let's say we're working under the modulo of 24, just going back to that example. 23 plus 4 is equal to 27, right? And 27 hours after today's midnight is 3 hours after tomorrow's midnight, so it's 3 a.m. So we say that 27 and 3 are equivalent under mod 24. So in other words, when working in modular arithmetic where the modulo value is 24, 27 and 3 belong to the same equivalence class. Going to a bit of a smaller example, if we work under mod 4, then we have 4 equivalence classes, 0, 1, 2, and 3. So the numbers themselves go under these equivalence classes, and then we repeat again. 4 goes under the equivalence class with 0, 5 with 1, 6 with 2, 7 with 3, 8, 9, 10, 11, etc. And then negative numbers also work similarly, like so. So you'll notice that if we take a number and we divide it by 4, the remainder is going to be equal to the equivalence class. However, you shouldn't think about modular arithmetic in this fashion. This is just how the operator works in most programming languages. This isn't really what the basis of modular arithmetic is. The core of it is just you have equivalence classes which are generally labeled from 0 up to 1 below your modulus, and all integers fall within these equivalence classes. Now, if you're wondering where floating point numbers go, like 1/2, they don't. Those don't exist in modular arithmetic. So what can you do with these? Well, most standard operations still exist. You still have addition. So let's say we're working with mod 12, so going to 12-hour time, for example. 9 plus 5 is equal to 14, right? Which is equivalent to 2 under mod 12. And so we can just say that 9 plus 5 is equivalent to 2 mod 12. So you may think of this as if we take the number 9 and add it to the number 5, we get the number 14, which is equivalent to 2 under mod 12. That's not exactly what we're doing, though. what we're saying is that the plus operator is defined between the equivalence classes 9 and 5, and when we combine the 9 and 5 equivalence classes with addition, we get the 2 equivalence class. So it would also be correct to say 9 plus 5 is equivalent to 26 mod 12. Because these both belong to the 2 equivalence class. So that's what the difference between actual modular arithmetic is and the modulo operator on its own. So that's what addition is. How about subtraction? Well, it works basically the same way. And I'll discuss later on a bit more advanced of a discussion about subtraction, because what I'm showing here is a bit simplified or reduced. 14 minus 5 is equivalent to 9 mod 12. And similarly, 5 minus 14 is equal to negative 9, which is equivalent to 3 modulo 12. And again, you should think of this from the perspective that if we take the 5 equivalence class and the 14 equivalence class, or in this case, this is actually just the 2 equivalence class, and subtract them, we get the 3 equivalence class. And if we were to do 2 minus 5, we would get the 9 equivalence class. For the last basic operator, let's talk about multiplication briefly. It also works very similarly. 5 times 7 is equal to 35, which is equivalent to 11 mod 12. And again, that should be interpreted as the 5 equivalence class and the 7 equivalence class, when multiplied together, yields the 11 equivalence class. So now how do you divide? Because we don't have fractions, we only have integers. So what would 3 over 4 be? For this, we'll need to move to a different modulus. So let's look at mod 5. So that's how division works. You might find this very confusing, and for good reason. Because, first of all, I just said that you don't have fractions. How does division work? And second of all, how do we get 2 of all numbers? But what is division, really? Division is just multiplication by the reciprocal. A divided by b is just equal to a times 1 over b. And what does 1 over b really mean? Well, for any number x except 0, x times 1 over x is equal to 1. So 1 over x is the number such that when it's multiplied by x gives 1. In other words, it's the multiplicative inverse. It is the multiplicative inverse, multiplicative because we're multiplying, and inverse because when you multiply by the original value, you get the multiplicative identity, which is 1, and it is named as such because 1 times anything is equal to the other side. So in this case, 4 times 4 is equal to 16, which is equivalent to 1 mod 5. Which means that 4 is its own multiplicative inverse. So 1 over 4, which doesn't really exist, is just 4 in mod 5. And so 3 divided by 4 is actually, what we're actually saying is it's 3 times the multiplicative inverse of 4, which is just 3 times 4, which is 12, which is equivalent to 2 mod 5. And so that's where this comes from. When we divide by a number, the division operation doesn't actually exist in modular arithmetic. We are multiplying by its multiplicative inverse, which is the value such that when multiplied by the original is equal to 1. There are many ways to calculate the modular inverse. I'm not going to discuss that in this video. I find that you generally don't really need it much. It's the other parts of this lesson that you'll need to use more often. But that's what division really means. It's multiplication by the multiplicative inverse. And notice that this isn't always well defined. What is 3, or what is the multiplicative inverse of 4 modulo 6? Well, it doesn't exist. It does not exist. Because if we take 4 and multiply by any number, we'll get another even number. And any even number mod 6 is going to be equivalent to either 0, 2, or 4. So it can't be equal to 1. So there is no value for which, when multiplied by 4, it gives 1 modulo 6. And so 4 does not have a multiplicative inverse modulo 6. So even though you might be tempted to say 4 divided by 2 is equal to 2 mod 6, that isn't the case. 4 divided by 2 is not defined mod 6, even though in standard arithmetic it would be equal to 2, which is its own equivalence class. It simply is not well defined in that particular context. Recall earlier that I said that we'd have to revisit subtraction at some point, because division is the opposite of multiplication. So to divide by a number is to multiply by its multiplicative inverse. Can't we say the same for addition and subtraction? And the answer is we actually can. Addition by a number is the equivalent, subtraction by a number is the equivalent of adding by its additive inverse, which is labeled negative a. And the additive inverse is defined such that a plus its inverse is equal to the additive identity 0. And it is named the additive identity because it doesn't change the value when you add it to something. In standard arithmetic, that's just the negative. So the inverse of 3 is negative 3, the inverse of negative 5 is positive 5. But you'll notice that we don't have negative numbers in modular arithmetic. The equivalence classes are just labeled from 0 up to n-1. And so the additive inverse is the number such that when added to the original gives the 0 equivalence class. So negative 3, or the additive inverse of 3, is equivalent to 4 mod 7. And this already probably makes sense to you because you'll notice that if you add or subtract 7, you stay within the same equivalence class. And so it's sort of the same thing as taking the remainder divided by 7. But that's sort of what subtraction really means. 5 minus 3, which we know to obviously be 2, is really the same thing as 5 plus the additive inverse of 3, which is 5 plus 4, which is equal to 9, which is equivalent to 2 mod 7. So technically, writing it out this way is a bit longer, but it's important to know that that's really how it actually works. Addition and multiplication are the two operations that are actually defined. Subtraction isn't really. It is addition by the additive inverse. Because again, remember that these are not really numbers. They are equivalence classes. They are just labeled numbers so that the arithmetic looks like it makes sense. So we're not subtracting classes. That doesn't actually exist. What we're saying is we have an operation called additive inverse that takes one class and transforms it into another. So modulo 7, the additive inverse of class 3 is class 4, and the additive inverse of class 4 is class 3. So quote unquote 5 minus 3 is the same thing as 5 plus the additive inverse of 3, which is 5 plus 4, which is the 2 equivalence class. Now let's talk about exponentiation. This is also an operation that exists, and it is just repeated multiplication. So since multiplication exists, exponentiation works perfectly fine. So for example, 5 cubed is 5 times 5 times 5, which modulo 7, 5 times 5 is equal to 25, so mod 7 that's 4. And 4 times 5 is 20, which modulo 7 is equivalent to 6. So 5 cubed is equivalent to 6 mod 7. And 5 cubed, in this case, the 5 is an equivalence class, but the 3 is actually just a number. Okay. So now we need to talk about two properties of there's only one property that we really need to talk about here, but first let's talk about the modulo operator in most programming languages. Because to apply this to programming, you'll need to sort of adjust, because the way it works in computing isn't with equivalence classes, they are actually just numbers. So there are two variations of the modulo operator actually. Python uses the first type, where a modulo b has the same sign as b. So let me pull up the terminal to show you what I mean. 4 mod 3 is equal to 1 as expected. And here what this means is the modulo operator takes the left side and transforms it into its equivalence class in modulo the right side. But what is 4 mod negative 3? This isn't really well defined in math itself, but we get negative 2. 1 is equivalent to negative 2 in the mod 3 class, and so 4 is equivalent to 1 is equivalent to negative 2. And so when the right side is negative, we use the same modulo, but we just map all the equivalence classes to the negative side. If we were to take negative 4 mod 3, we would get positive 2, because negative 4 is equivalent to negative 1, which is equivalent to 2. And if we take negative 4 mod negative 3, we just get negative 1. So this makes sense. Now how does it work in JavaScript? 4 mod 3 is the same thing, but 4 mod negative 3 is still the same thing. Why is that the case? Well, in JavaScript, the modulo operator keeps the sign of the left side. It's more of a remainder. If we take 4 and divide it by negative 3, we get negative 1, remainder 1. And so it gives the actual remainder under division, because 4 divided by negative 3 is equal to negative 1, remainder 1. So the remainder is 1, which is equivalent to negative 2, but in this case, it would give the sign of the left side. So if we take negative 4 mod 3, we get negative 1. Because the left side divided by the right side, negative 4 divided by 3, is equal to negative 1 remainder negative 1. And finally, negative 4 divided by negative 3, that one still gives negative 1 as expected. So you should be aware of which one your language uses. Most of the time, you'll only be working with positive numbers on both sides, but sometimes your left side may be negative, and if you just follow Python guides, you might end up with weird errors because you're getting a negative output, so you have to be careful with this. The way you can sort of solve this is, you'll notice that if we take the modulo, the absolute value of the output cannot be larger than or equal to the absolute value of the modulus, the right side of the operator. So if we take a number and mod the right side, and then we add the right side, and then mod again, we will get the same sign as the right side. Let me show you why that's the case. Negative 4 mod 3 is equal to negative 1. This value cannot possibly be smaller than or equal to negative 3, otherwise it would get wrapped back up. Now we take this and we add 3. So since this part could range from anywhere from negative 2 up to 0, so that would give us 0. If we add 3, now it goes from, previously it was negative 2 up to 0, and now it goes from 1 up to 3. So this isn't quite right, because we might get 3 in this case, which isn't really valid, so then we have to do modulo 3 again. And so that's how we would get Python-like. We do x, y, and we return x mod y plus y mod y. So that's our function. So if we do f of negative 4 and 3, we get 2. And similarly, if we do f of 4 and negative 3, we get negative 2. I believe C and C++ also use JavaScript similar operator. So does Java, I think. You should check for the language you're using though. So those are the two variants of modulo. And for the remainder of this, we'll only be talking about the Python type. But actually it shouldn't matter because I think I won't be using negative numbers. So let's talk about a property that comes from modular arithmetic itself. So I already went over this concept in my day 11, 2022 day 11 walkthrough, but here's where the origin of this property is. So just looking in code, I'll write my code out in blue just to make it clear what's code and what's math. A plus B all modulo M is equal to A mod M plus B mod M all modulo M. And by the way, the modulo operator has the same precedence as multiplication and division for most languages. So when paired with multiplication or division, it goes left to right, and it happens before addition, but after stuff like exponentiation. So why is this the case? Well, what we're saying is A plus B is equivalent to A mod M. This part doesn't really exist in math, so let me write it out in blue. A mod M plus B mod M under the equivalence class of modulo M. So hopefully it should make sense why this is the case. The modulo operator always keeps things within the same equivalence class, right? And so what we're saying is the equivalence class of A plus the equivalence class of B is equivalent to the equivalence class of A plus the equivalence class of B. This thing here doesn't actually even do anything in actual modular arithmetic. So long as we have this modulo M at the end to get it all into the to all map it back to the base equivalence class, these modulo M's will not change which equivalence class this value is in. So in other words, these two values are in the same equivalence class, and these two values are in the same equivalence class. So even though A plus B and A mod M plus B mod M will be different numbers, they were the sum of the same two equivalence classes. So they will also be the same equivalence class. So when we use modulus M to get them to their equivalence class forms, the output will be the same. So if you're doing addition of a bunch of large numbers and then want to get the result mod M at the end, you can take the modulo of all of the intermediate values and also modulo each time. So what that might look like is this. So let's do an example in JavaScript because I know JavaScript can run out of space for integers. It doesn't have infinite precision integers unless you use the big int class. Let's say we want to add 2 billion to itself 1,000 times. I don't know if this fits. Let me check. So that's 2 billion. Okay, I'll need to do a larger number then. Yeah, you'll notice that this starts to get rounded off. I don't know how to prove that this isn't actually precise, but either way, just for demonstration, let's say we have an array. Actually, there's no need for me to demonstrate why this might be necessary. I'll just demonstrate why that is actually equivalent. Let's say we have an array, and we want to find its sum modulo 5. So x dot reduce xy to x plus y, that gives us the sum. And you'll notice it's 31, which is equivalent to 1 modulo 5. If we instead took the modulo of the intermediate steps, we would get the same outcome. Because what we're essentially doing is, instead of 1 plus 3 plus 2, etc., we're doing 1 plus 3 mod 5 plus 2 mod 5 plus 7 mod 5, etc. And so all of these intermediate mod 5s do not affect which equivalence class all of the values before them are in. and so it will not affect the actual answer at all. Here's where this gets more interesting though. And it's not actually that much more interesting, but this fact is a lot more useful because numbers tend to blow up a lot more when this happens. The exact same applies for multiplication. Because again, we're in the same equivalence class. These modulo m's don't actually do anything on the math side because they're always in the same equivalence class. So since a and a mod m are in the same equivalence class and b and b mod m are in the same equivalence class, then their product will be the same equivalence class. So when we call modulo m, we will get the same output. This one is a lot more useful because multiplication tends to cause numbers to blow up a lot faster. If you multiply by 2 each time, the output grows very large very quickly. Let's just do an example. So in Python, let's start t out equal to 5, and let's say we want to multiply it by 2 1,000 times, and then modulo 7. So if we double t 1,000 times, t is now equal to this number, which is very massive and doesn't fit within most programming languages' integers. And if we take t modulo 7, it's tiny. But if instead we do t equals t times 2 mod 7, we moduloed in each intermediate step and still got the same answer. To show why this is necessary, if we let t equal 5, and for let I equals 0, I less than 1,000, I plus plus, t times equals 2, t is this number. And if we take it modulo 7, oh, I'm honestly surprised that even worked. Let's add another 0. Okay, now t is infinity, because it's gotten so large that JavaScript's no longer capable of handling it, and it just goes to infinity. And if we do mod 3, it doesn't even work, because what is infinity mod 3? So if we go back into Python and multiply t by 2 10,000 times, t is extraordinarily massive. And modulo 7, it's equal to 3. It's still tiny. So now if we go back into JavaScript and do the same thing, but this time we modulo in between, now we get our answer. T is equal to 3. It works perfectly. So taking the modulo in the middle, first of all, it means that your numbers will actually fit. Second of all, even if you're working with a language like Python, when the numbers get this large, operations can start to become extremely slow. And so if you're doing this a lot, first of all, you might actually run out of memory. Like on day 11, if you do it the naive way, even if you use infinite precision integers, the numbers don't fit within the universe. They're so large that the representation could not even physically fit within the universe. But by taking modulo in between, you keep them very small. And the final property that went into day 11, which is also important to know, is the invariance of divisibility. So one important thing to note is that if n is equivalent to x mod m, where n is some number and x is the equivalence class represented by a number, then n is equal to km plus x for some integer k. What this means is it's x larger than a multiple of m, because km is some multiple of m. So let's say n is equivalent to 1 modulo 4, then what could n be? Well, km plus x is equal to 4k plus 1. So going through all the values of k starting from 0, we have 1, 5, 9, 13, etc. And going down, we have -3, -7, -11, etc. And you should be able to easily see that these are all equivalent to 1 mod 4. And so, the important property that I'll write out first is that x modulo p modulo q is the same thing as x modulo q if q is a factor of p, or p is a multiple of q. Why is this the case? Well, x mod p, where p is equal to, if p is a multiple of q, then p is equal to kq, where k is some integer. So x mod kq is in the same equivalence class modulo kq. So in other words, if x mod kq is equal to n, that means is that x is equal to t kq plus n, where t is some integer. So t this time is our multiple factor. Now what happens when we modulo q? Well, x is also equivalent to n mod q, because it is of the form something times q plus n, where in this case this something is equal to tk. Since t is an integer and k was an integer as defined here, then tk is also an integer. So x is also equivalent to n mod q. So what this means is that if we take x and find an equivalence class in a multiple of q, then it will still be in the same equivalence class as it originally was in q itself. And so that's where the trick for simplifying day 11 came into play. So for day 11, and by the way, if you're not sure what problem 11 is, you should probably, actually, just to avoid spoilers, I'm not going to talk about problem 11 here. But what this means is that if you want to take a number modulo 3, and you also want to be able to check it modulo 7, then if you keep moduloing it by 21, you won't change the value. So let's say we have a value, let's go back into Python. Let's say we have a value 532. Modulo 3 is equal to 1 and modulo 7 is equal to 0. But what if this number were really large and we didn't want to have to store it, especially if we're constantly multiplying it by stuff? If we take it modulo 21 and then modulo 3, we get the same result as before, and same with 7. As another example, x mod 3 is equal to 0 and x mod 7 is equal to 3. So we take x mod 21, we get 3. These examples are terrible. I don't understand how I'm getting this unlucky with my examples. Let's pick larger moduluses. X mod 11 is equal to 9 and x mod 13 is equal to also 9. So we take x mod 11 times 13 because that is a multiple of both of them. Okay, I really should have picked these examples ahead of time because these are horribly unlucky. Okay, there we go. So x mod 13 is equal to 9 and x mod 17 is equal to 15. But x is somewhat large, so what if we didn't want to have to store this entire thing, but we still wanted to check what it was mod 13 and mod 17? Well, if we take it mod 13 times 17, which is equal to 221, then if we take that value and modulo it by 13, the value does not change. And if we take it mod 17, the value still does not change. So that's the crucial part for this property. If you want to check modulo q, as long as you modulo it by something that's a multiple of q, it won't change the result. And so if you want to check by a bunch of q's, you just need to find something that's a multiple of all of them. The product works. The LCM, or the lowest common multiple, is of course the smallest, but the product will work. And if all of your q's are distinct prime numbers, the LCM is just their product. Finally, we have one last thing that we need to discuss. It's the exponent operator. Because we've already sort of touched on this. Remember what I said about multiplying 5 by 2 10,000 times and then checking it modulo 7? That was the same thing as saying 5 times 2 to the power of 10,000 mod 7. And that is what's called modular exponentiation. Let's get rid of this 5 times. Modular exponentiation. It is exponentiation under a modulus. So exponentiation blows up pretty fast. You could even say at an exponential rate. And so representing the whole thing and then doing modulo at the end is pretty impractical. And this specific thing has shown up in previous Advent of Code problems, and I'll go over one in a bit just to sort of solidify the point. So we already went over the naive implementation. Just run a loop through this, and each time we just take the modulus in between. However, that still requires us to loop by this. So what if we wanted to take 2 to the power of 1 billion modulo 7? If we do this in Python, it should still work. It might take a while. If not, I'll just increase the number. So total starts at 1 for blank in range 1 billion. T equals t times 2 mod 7. Sorry, I forgot to close back. You'll see that it's running for a while. Even though we're taking the modulo in between every time, so the value isn't really blowing up, it still takes a while to loop a billion times. That's where another property of arithmetic comes in. And this is general to all arithmetic. If you have some base b and take it to the power of x plus y, that is equal to b to the power of x times b to the power of y. Why this is important is if we want to take b to the power of 13, that's equal to b to the power of 8 times b to the power of 4 times b to the power of 1. Now why did I split it up this way? Well, these are all powers of 2, right? In fact, 13 in base 2 is equal to 1101, representing 8 plus 4 plus 1. Why is this important though? B squared is equal to b to the 4. B to the 4 squared is equal to b to the 8. B to the 8 squared is equal to b to the 16. So you'll notice that we only need to compute log 2 of the exponent number of different things to get all of the binary ones. And then we just need to combine the appropriate ones together to get the appropriate value. So what that means is we can take 1 billion, convert it into its binary representation, find all of those, find b to the power of all of those powers of 2, and then just multiply together the appropriate ones. So for this, I don't want to do this in the terminal. I'll open this up and try it online. Let's define a function that takes a base, an exponent, and a modulus, and computes b to the power of the exponent mod m. And so just as a sanity check, 2 to the power of 20 mod 17 is equal to, let's pick a different example, 13 is equal to 9. So f of 2 to the power of 20 mod 13 should be equal to 9. So how do we calculate this? Well, we want to convert it into its binary representation and then multiply by the appropriate numbers, right? So this is a bit hard to explain exactly why we can do this, but what we'll basically do is we'll keep dividing the exponent by 2, and each time we'll check if it's odd or even to decide if we multiply. So let's take 20 as our example. So there's a trick for converting numbers into binary on paper, which will play into this algorithm significantly, so let's go over it. If we want to convert 20 into binary, we take it and we divide it by 2. It's equal to 10 remainder 0. 10 divided by 2 is equal to 5 remainder 0. 5 divided by 2 is equal to 2 remainder 1. 2 divided by 2 is equal to 1 remainder 1. And 1 divided by 2 is equal to 0 remainder 1. And so once we reach 0 here, this is 1 remainder 0. Once we reach a 0 here, we stop. And so if we take these numbers and read them bottom up, we get 10100 base 2, which is equal to 20. We see that 20 is equal to 16 plus 4. Now, why did this work, though? Well, we know that if a number is odd, then the last digit has to be a 1, and if it's even, the last digit has to be a 0, right? Because all of the previous digits represent even numbers, 2, 4, 8, 16, 32, etc. All of those are even. Only the last digit is a 1. So when we divide it by 2, if it's odd, the remainder will be 1, which means that the last digit has to be a 1. If our number was even, then the remainder will be 0, so the last digit needs to be a 0. And then we observe that x is equal to 2 times x over 2 plus x mod 2, where this here is the floor-to division. And here's another important thing to notice. When you multiply a number by 10 in base 10, you put a 0 at the end. When you multiply a number by 2 in base 2, you also put a 0 at the end. And so what we're saying is we're taking x, we're splitting it into x divided by 2 and x mod 2. X mod 2 represents the last digit, which is either a 0 or a 1. And x divided by 2 will give us some number that we then multiply by 2. And then we add these together, like here, to get x. So what that means is that when we take it mod 2, we get the last digit, and then we divide it by 2, rounding down, and then we repeat the same operation again, take the binary representation of that, shift it to the left by 1, and then add the 2 together, which is the same thing as saying we take this digit and we tack it on to the end of the binary representation of x over 2. Now, the reason that's important is because this means that we don't actually need to convert our number into binary. We just need to repeatedly go through these, but we don't actually need to store the digit list. Because our exponent is starting from 1 and then increasing up 2, 4, 8, 16 anyway. So we don't actually want the binary representation from the higher digit down. We actually want it in reverse order, which works perfectly because it means that at each step, we take x mod 2 and check if it's 1 or 0 to determine what the digit at that position would be. If it's a 1, then we take our total and we multiply it by the base to the power of whatever the power of 2 we're at currently is. And if it's a 0, then we don't do that. And then we can divide x by 2 and increase the exponent on p, the exponent on b, and repeat the same process. So let's see what this will look like in code. I will implement this in JavaScript as well. So the total starts out equal to 1. Let's just ignore the modulo for now. While the exponent is greater than 0, if the exponent mod 2 is equal to 1, then we will multiply t by the base to the power of the exponent. And I'll just put b here, because instead of actually increasing the exponent, we'll just multiply b by itself. Because the crucial fact that we're relying on is, remember this part. Each time we square b, we double its power. So now we will just square b. And we also need to remember to divide e by 2. And so long story short, what we're doing is this line checks what the digit at this position of the binary representation of e would be. This multiplies by b to the power of p, where p is the next power of 2. But we don't really keep track of what power we're on. We just square b each time, which doubles the power on it. And then at the end, we return t. So we do this, we get 1048576, which is equal to 2 to the power of 20. And so we just take that modulo n. But the whole point in doing this was that we don't want to have a large number in between. So we can actually stick a t mod equals m right here. And this means that our number will never blow up. More crucially, it means that we can take the exponent of a very large number in comparatively quick time. It's still going to take a while. Oh, sorry. Another thing I forgot to do. Yeah, so t is being multiplied by b, which means that t can be modulated by m in the middle, but it also means that b can be modulated by m in the middle. That is also crucial, because otherwise b will blow up. And yeah, this finishes instantly. We just computed the power, 2 to the power of, that's 2 to the power of 1 trillion instantly, because we're under modulo 13. That's how powerful modular exponentiation is. Now the neat thing about Python is you actually don't need to implement this function because it's already a built-in. It's called pow, and it already allows you to give an optional modulus operator. So pow takes at least two arguments, and takes the first one to the power of the second one. And optionally, you can include a third operator, which will be the modulus, and it will automatically do fast modular arithmetic for you. It's JavaScript that I don't think supports this. JavaScript does have a built-in power operation, I think, but it does not accept a modulus. So you would have to implement that yourself, I believe. And so in JavaScript, this is what it would look like. And so that's how it would look in JavaScript. And you can implement similar things in all sorts of other languages. The core logic works the same way. If you want to optimize this slightly, instead of dividing by 2 and then flooring, you can actually right shift. So the right shift operator literally is what it describes itself as. So right shifting by n means you take the binary representation, you shift it to the right by n, and all of the digits that were within the last n just get discarded. And so this is the same thing as floor dividing by 2, because we just shift to the right, and then whether the last digit was a 1 or a 0, we just drop it regardless. And so that would be slightly faster. And so if you want to optimize, you can do right shift equals instead of divide equals. It's also just easier, especially in languages that don't have floor division like Python does. All right, and so for the last part, let's just go over a problem where this is required. 2015, day 25. So the core of the logic is you have a bunch of codes that are printed on an infinite sheet of paper starting in the top left corner, and they're filled in diagonals starting with the first row and then the filling diagonally to the up and to the right. And this process is repeated until the infinite paper is covered, whatever that means. So this is how the first few numbers would be present. And so your puzzle input is which position you need to output. So in my case, it was row 2981 and column 3075. The first thing we need to figure out is what position on that page is, so which number would be here. So the way we do that is we notice that the diagonal, which diagonal we're in, so this is the first one, 2, 3 is the second one, 4, 5, 6 is the third one. The diagonal number we're in is one less than the sum of the row and the column. So notice that along a diagonal, the sum of the row and the column are the same. In this case, it's 7, here it's 6, here it is 3. And so this is diagonal number 2. Which means that what we actually want to do is first of all, compute how many numbers are in the diagonals above ours, and then add on our column number, because that's our position within our current diagonal. To compute how many are in the sum of all of the diagonals above us, it's really just 1 plus 2 plus 3 plus 4, etc. But if you know Gaussian addition, then you can actually do that instantly. If you don't know that, here's a bonus little tip. I know this lesson was supposed to be about modular arithmetic, but here's a bonus thing. 1 plus 2 plus 3 plus 4 all the way up until n is equal to half of that entire sum plus that entire sum again. And you would obviously think, well, that is completely obvious. What's the point? The point is that we can line up our additions like so. And the reason we want to do that is because each of these terms is equal to n plus 1. So it's 1/2 of n plus 1 times however many times it shows up. And it obviously shows up n times, so it's n plus 1 times n. So this is equal to n times n plus 1 over 2. So that's how to derive this formula. The sum of all the positive integers from 1 up to n is equal to n times n plus 1 over 2. So what that means for this problem is that if we're in the nth diagonal, then the number of numbers in all of the diagonals above us is 1 plus 2 plus 3 all the way up to n minus 1. Which would be this formula but applied to n minus 1. So it's n minus 1 times n minus 1 plus 1 over 2. In other words, it's n times n minus 1 over 2. So in this case, n is our diagonal number, which we already established was the row number plus the column number minus 1. So r is equal to 2981 and c is equal to 3075. Now, r plus c minus 1 is our diagonal number. We'll call it n. And n times n minus 1 over 2 is the number of the number of places in all of the diagonals above ours. And finally, we just need to add our column number. So this thing plus c is our position. You'll see that if we do the same thing for the example, so let's just put it here. R equals, let's take this for example. So the row is 3 and the column is 4, n is equal to r plus c minus 1, print n times n minus 1 over 2 plus c, we get 19, which is the value of this here. So that's the position. Now let's look at what we do with that. The voice on the other end tells you how the codes are actually generated. The first code is 20151125. I don't know why it's not 1225. I think there's a specific reason for that. After that, each code is generated by taking the previous one and multiplying it by 252533, and then keeping the remainder from dividing that value by 33554,393. So it's multiplication followed by modulo. So to find the second code, we do that. To find the third code, we do that again. And so it's asking us what code comes at the position specified. So what is the 1833156 code? Well, if we did that with a trivial loop, it would actually finish and it wouldn't take all that long. But we can do it with modular exponentiation, because what the problem is asking us is the starting value s times the factor f modulo m times f modulo m times f modulo m, etc. And since the modulo m doesn't do anything when we're working in the equivalence classes mod m, that's the same thing as s times f times f times f, etc. And since we started with the first value as s, this is equal to s times f to the power of n minus 1. Or sorry, I should call that k minus 1, where k is our position. And so it is fs times f to the k minus 1 mod m. In other words, it is 20151125 times the pow operator on the base, which is 252533, to the power of our above value, let's call it k, 20151125 times pow 252533 to the power of k minus 1 modulo 33554393. And then we just take that value and modulo it by 33554393 again to get our answer of 913260. And so we could just do this with a naive loop, but using fast modpow, we can calculate this instantly. So that's an example of where modular exponentiation is highly useful. I believe there are some problems where it was strictly necessary, but I can't think of one immediately. So let's just quickly recap all of what we went through. The first is the basics of modular arithmetic. Instead of numbers, you have equivalence classes from 0 up to n minus 1. Addition works very similarly. You just add the numbers of the equivalence classes and then take the remainder. That's sort of the not really mathematical way of doing it. Multiplication also works the same way. Subtraction exists, but is actually the addition of the additive inverse. Division doesn't exist, but we use the multiplicative inverse. So if we wanted to take 3 divided by 4, that's really the same as 3 times the multiplicative inverse of 4, where the multiplicative inverse is the number such that when multiplied by 4 gives 1 in our modulus. So in this case, since 4 times 2 is equivalent to 1 mod 7, then the multiplicative inverse of 4 is 2 when working in mod 7. And so 3 times the multiplicative inverse of 4 is equal to 3 times 2, which is equal to 6 mod 7. So 3 divided by 4 would be 6. Exponentiation also works fine because multiplication is defined, so the exponent to the power of n is just that number multiplied by itself n times. There are 2 variations of the modulo operator in programming, so you need to be careful with which one you have. One of them will use the sign of the right value, and one of them will use the sign of the left value. Python's is this one, JavaScript's is this one. Also, if we take n modulo p and then modulo q, that is equal to n modulo q, so long as, or if and only if, q divides p, so p is a multiple of q. This part is important. This does not work otherwise. And finally, we went over we also have the fact that a plus b mod m is equal to a mod m plus b mod m all modulo m, which works because this doesn't change the equivalence class we're in. And this also works with multiplication the exact same way. And finally, we talked about the modpow and how to do it the naive way, but also how to do it the more intelligent way by using binary deconstruction to avoid having to loop the same number of times as our exponent. And finally, we went over a quick solve of 2015 day 25, both including a bonus with the Gaussian summation thing, getting our position, and then we just need to use modpow to figure out what the key at that position is. So thank you for watching until the end of the video. If you did, I hope you enjoyed this video and learned something from it. If you have any questions, do feel free to leave it in the comments below. And please do leave any suggestions if you have other topics that you want to go through. Since modular arithmetic did come up in day 11 and has been important in the past and might be useful in the future, again, I figured I'd dedicate an entire video just to talking about the actual principles behind it, some of the properties, and how to apply it to coding challenges like this. So thank you for watching, and I'll see you next time.